Okay, this is the fourth video in the Algebraic Methods playlist / chapter. Today we're going to be talking about partial fractions. This is one of those kind of niche chapters that it's a very specific skill you need to learn, but I am covering it in its own video because it does come up quite a bit, and they say here in the textbook even it comes up in binomial expansion and integration. Right here it doesn't look like it's really coming up in a whole lot, but trust me, this chapter 11 integration, this is going to be a big skill that you need to learn. So let's get straight into it. Single fraction with two distinct linear factors in the denominator can be split into two separate fractions with linear denominators. This is called splitting into partial fractions. Yeah, that about sums it up. There are two methods by which constants a and b can be found: by substitution and by equating coefficients. Yes, although you can basically do a combination of these two, and I'm gonna show you exactly how we actually do this. So as a first example here, we have x plus 1 and x minus 4. Note that they use the identity notation here. This is not an equation, this is an identity. And what that means is that there is some way in which we can rearrange this to always fit into this exact form right here. That's what the identity means. And that's helpful because what that means for us is we just need to manipulate this to somehow fit into this mold here. So we're actually going to do the opposite. We're going to start with this form here and then see how we can take this and make it look like this. So if we start with, because we have just a general form here, we don't know what a and b are. So we start with a and b. Now, when we add fractions, we know that they have to have the same denominator. So to get the same denominator here, well, this has x plus 1 and this has x minus 4. So the way we get them to have the same denominator is to have them both have x plus 1 minus x minus 4. In other words, we're multiplying this by x plus 1, top and bottom, and we're multiplying this by x minus 4, top and bottom. Okay, and when we do that, we get that a lots of x minus 4 plus b lots of x plus 1 divided by x plus 1 times x minus 4 is equal to this here, these partial fractions we had before. And what can you tell me about this complete form that we have here? Well, it looks strikingly similar to what we initially had with the 5 over x plus 1 times x minus 4. And that is because these are in fact the same exact thing, hence the identity. So, knowing that, we can essentially just equate 5 to x minus 4 plus b lots of x plus 1. Great. And from this, we can find out what both a and b are. This is where the substitution comes in. So we can essentially say that x could be anything here, right? And we want to use some example. X could be literally anything, but we want to use an example of x for which we can eliminate either a or b. The reason for that is, well, right now we essentially have what kind of looks like one equation with two unknowns. It's not exactly that because x could be anything. So I'll give you an example here. 4x equals, remember, we want to cancel out one of these. The way we cancel out one of these, well, a times 0 is 0 and b times 0 is 0. So we want one of these here to be 0. There's two ways that could happen. X could either be 4 or x could be minus 1. By the way, this is completely arbitrary. You don't need necessarily to equate them to 0. You could just use x is 1 and x is 2, and you would end up with two equations that you would have to solve simultaneously. But this way, you kind of shortcut that, and you can straight away find out what a and b are. Okay, so for x equals 4, we have that 5 is equal to a lots of 4 minus 4 plus b lots of 4 plus 1. Okay, so this is 0, these cancel. This is 5, which means that 5 lots of b is equal to 5, and b is equal to 1. That's our first answer. Then for x equals minus 1, a lots of minus 1 minus 4 plus b lots of minus 1 plus 1. This is 0. This is minus 5, therefore a is equal to, sorry, minus 5a is equal to 5, and a is equal to minus 1. Now, it doesn't matter which order you put the a and b. In the question, they've shown you, they've given you an example. They say a over x plus 1 and b over x minus 4. You could, for example, have a over x minus 4 and b over x plus 1. It doesn't actually matter. But you need to be self-consistent. So here, where we have labeled a as being the numerator of this x plus 1, we need to just keep that consistent. So when we sub this back in, we say that 5 over x plus 1 times x minus 4 is equal to minus 1 over x plus 1, because that's what we had initially as a. So as long as you're consistent, it doesn't matter. And that's our answer there.